This example is a boiling point trend explanation, and it is of the dipole-dipole force type. In this example, we're asked to explain the boiling point of silane, phosphine, and hydrogen sulfide. SiH4, which is your first green bar, has a boiling point of approximately 155 Kelvin. Phosphine, which is the second green bar, has a boiling point of approximately 170 Kelvin. And hydrogen sulfide, the third green bar, has a boiling point of approximately 210 Kelvin. In this example, we're going to again follow the strategy of thinking about London dispersion force first. So here we have silane SiH4. If we count up the number of electrons, it's 14 for silicon and 1 each for 4 hydrogen, which gives us a total of 18 electrons. In the phosphine, the pH 3, we also have 18 electrons, and H2S is 18 electrons. We describe these three compounds as isoelectronic, and therefore they have approximately the same London dispersion force. So London dispersion force is not causing the difference in boiling point among these compounds. When this happens, we need to go to our next force, dipole-dipole. Although it is smaller and generally not as important, when we have a tie-break situation like this, this is exactly where we should go. Before I do that, though, I'm just going to check for the hydrogen bonding force, because we know that's the other big one and a game changer. We have hydrogen in all these compounds, but it has to be HNOF, hydrogen bonded directly to nitrogen, oxygen, or fluorine. The hydrogen here is not bonded to N, O, or F, so there is no hydrogen bonding here at all. So any changes must be due to the dipole-dipole force. Now remember, dipole-dipole force only exists within polar molecules. So we have to think back to our Lewis diagram, shape, polarity. SiH4 is tetrahedral and symmetrical, so there is no dipole-dipole force here. pH 3 is asymmetrical and it is polar, but when we check the electronegativities of phosphorus and hydrogen, they're both 2.1. So it's not getting any additional help from the phosphorus to hydrogen bonds. So we would describe this as slightly polar. H2S, however, does have polar bonds. There is a difference in electronegativity for the phosphorus and the hydrogen of, I think it's 0.4. Sulfur is 2.5, hydrogen is 2.1. Yes, there's a 0.4 difference in electronegativity of those two atoms, and it's a bent shape. So it is an asymmetrical shape, has polar bonds, so this one here is polar. So the one that is the most polar, the H2S, would be expected to have the highest boiling point, and it does. We see that for these three, there is a trend here as the polarity increases from non-polar to slightly polar to more polar. We also see a corresponding increase in boiling point. So these isoelectronic compounds have similar London dispersion force. We know that counting electrons is just an approximation. It also is influenced by shape. So we'll say similar LDF. So the differences are due to differences in polarity and dipole force. H2S is the most polar, and has the highest boiling point. SiH4 is nonpolar and has the lowest. So again, London dispersion force is approximately tied because all these compounds have the same number of electrons, or isoelectronic. The difference, because there is no hydrogen bonding, must be due to the dipole-dipole force. The nonpolar one has no dipole-dipole and has the lowest boiling point. The most polar has the highest boiling point.